as if before the first line of your code executes, way up here, someone put all this code in for you into Python and created a thing called max for you. Now we've been using this already, built-in functions, we've got type conversions, we've got like the float that takes a integer and returns a floating point version of that. And again, this is kind of like an expression. So it's like I want to divide this by 100, but before I do that, I've got to convert it to a float. So it has to sort of do these function calls as it's evaluating the expression. Okay? Sometimes, like here, we just have a prints out the return value. That's what this is. This is the return value. If you just type a function in a parameter, it can be in a constant or it can be a variable. And as we'll see in a second, we'll give you many of these if you like. So you can either just run it or take the result of this. This passes an integer in, converts it to a float, and then puts the float into that. Type tells us what kind of thing that is, and you can use this inside of an expression. And so it's like, what am I going to do first? Oh, I've got to do 2 times this thing. Oh, wait a sec. Pause just briefly for a moment to call out to some float code, pass a 3 into it, and then something comes back, the return value, the residual value comes back, and then that participates. In this case, it's going to be 3.0, participates in this 2 times 3.0. Okay? And so 2 times 3.0 then ends up being 6.0, et cetera, et cetera. But you can see as it's like, oh, wait a sec, I got to figure out what this is, call the function, get the return value, and then continue processing this expression. We've also done this with string conversions, partly because, just as an example, the input always returns a string. The input function returns a string. And so, you know, here's this string, could be coming from input, but we'll just take 1, 2, 3. We know that that's a string. It's not the number 123. And if we try to add 1 to it, we get a traceback. Cannot concatenate string and integer. Traceback. But we can't convert that string to an integer. And so int can take like a floating point number or an integer or even a string, and it says, oh, I know what I'm supposed to do with a string. I'm supposed to look at this, interpret these as numbers, and, you know, multiply by 10 and figure out what the hundreds place is and all that stuff. There's a little bit of work to that, and it does it. But then it gives us back an integer, and we say, oh, what is that? That's now the 123, but it is of type int. And now we can add 1 to it and get 124. And as before from this example that we're kind of reusing from a previous chapter, you don't want to try to convert, oops, sad face, sad face, sad face. Don't want to try to convert something that doesn't have digits using int, because it'll say, I don't know what to do, and then your program quits, right? You don't want your program to stop, tracebacks, and you can, of course, deal with that with try and accept, but that's like a previous lecture. Okay, so up next we're going to talk about building our own functions, not just using the predefined ones. So welcome back. We're going to continue and start talking about building our own functions. So again, we use the def keyword to define a function, and then later we're going to invoke this. And there's a bit to it. We are defining the name of the function. In effect, we're extending Python and creating new predefined things that we can use, except it's our code. It starts with a def keyword, has some optional arguments, which we'll see in a bit. That's what the parenthesis is. And then the name. And the function names follow the same rules as variable names. And then you have an indented block, whatever code you want to do, and then you have a de-indented block, and that sort of defines the essence. The key thing here is this is not calling. It's not invoking. It's not executing. It's remembering. It's storing. It's figuring things out. So here is the output of a program that defines a function but then doesn't use it. So this is a sort of broken function. So here we go. We start x equals 5, print. You don't have to you have all the defs at the beginning. The def runs whenever. So, you know, out comes hello. And then we define a function, and this says, oh, you want to make a new thing here. So I'll make a new thing. It's kind of like a variable in a sense. And then it copies this stuff, copies it up there, and says, later you probably are going to want to use this, so I'm going to remember it. So it doesn't do anything there. No output comes out. Then it says print yo, and out comes yo. And then it adds 2 to x, so x is now 7, and then it prints x, and there's no 7. There's 7. These print statements never ran. They never ran. Why? Because we did not invoke them down here. We defined them but didn't invoke them. So let's take a look at how you invoke a function, right? You define it and then you use it. Sometimes you define it once and use it once, but more commonly you define it once and use more than one time. Again, the store and reuse pattern. The def is the store and the invoking is the reuse. So here's just a slightly different version of that last program, and so now it's going to actually invoke it. So x equals 5, print hello, def, so out comes hello. This produces, the def produces no output, right? But because there's a D indent here, that is the entire blob of the code that is part of print lyrics. So it prints out yo, and now we're going to invoke. This is the call. We're going to call the function. Now the function goes up. Let's clear this. So we're down to here. Now this like suspends at this place. It's like remember to come back to here when we're done. Go up, run this code, and then come back, and then continue on. So it like leaves like a breadcrumb of where it's supposed to come back to, and then it runs, and then the print lyrics, of course, produces the 2 lines of output, and yeah, that should probably not have. That day should be up there, and then x equals x plus 2, which makes it 7, and then prints out 7. Okay, so this is the invoke or call the function. Okay, you defined it, and then later you called it. Now, in addition to just call and return and invoking, we can pass parameters in. And the example of the parameter is in the max function, we have to say, this is the thing I want you to find the maximum of, the largest thing. And part of it is in the whole store and reuse pattern, we have a few lines of code, but sometimes we want to do ever so slightly different things in the different invocations. And so we use the arguments to subtly adjust, like finding the maximum is a general thing, but what thing to find the maximum of, that makes a function that's much more useful and reusable in a lot more situations. So arguments are the thing we passed in, and we define for our functions that we're going to build, we, on the def statement, so we say def, greet, name a function, and then this is the arguments, the things that are coming in. Now this lang variable, in a sense, only exists during the life of the function, and it represents sort of a placeholder. It's not a real variable in the same sense. It's a placeholder that refers to how you touch that first parameter that's sitting in there. Okay, and so lang is our first parameter, whatever it is. We don't need to see this part down here right now. All we know is we're going to make a function, and we're going to take a parameter, and this lang is the placeholder that tells us what that parameter is. Okay, so within the function, we're going to check to see if the language is Spanish. If we are, print hello. Else, if the language is French, print bonjour. Otherwise, print hello. We have a very highly simplified language translation system here. So the def, of course, does nothing except remembers that and defines the concept greet. So that comes down, and now we're going to call it. And that says, go look up the thing that I defined called greet. If you don't put this in, greet is going to give you a traceback. But because you extended and named it greet, so it runs in, it starts, suspends the code here, starts up here, but then lang is now an alias to en. So now we can run if that is es, else if, I'm getting it all wrong now. Right, so en comes in as lang, we're coming in the code. If it's not es, it's not fr, else it prints hello, and then it comes back to the next line. And then we call it again, and this time es is lang, and so it runs this code and prints hola, and then next time it calls with this, and then it prints bonjour. You get the idea. So this is a placeholder so that on the successive calls or invocation of the function, we can get at whatever the programmer put in as that first parameter. And so we are saying in this definition, we are ready to receive a first parameter. Please call us with a parameter and then we will be able to do something slightly different for the different values. So this is a reusable bit of function that prints hello in 3 different languages, and then we tell it what language at the moment that we're actually invoking it. So that's putting stuff into the function. Now getting stuff back out is the concept of returning. In the return statement is an executable statement that does 2 basic things. The first thing that it does is it finishes. Now this is a 1-line function, so that's kind of redundant, but when Python goes into the return statement, it doesn't continue on to the next line. It just returns. That is the end of the invocation of that particular function. But even more importantly, it takes as its parameter. You can say return without a parameter, and it will stop the execution of the function, kind of like a break does for a loop. It's kind of a break for a loop. Get out, we're done, don't run that next line, get out. But it also allows the specification of what you want as the residual value in an expression. So we're doing a print, and then we're saying greet, and what's going to show up here is whatever this function does in its return statement. And so that prints hello. We call it again, and it prints hello again. Okay, and so basically the return statement is I call this the residual value. It's like what shows up here when the function is all done, and it's the string hello. We call the functions that return values fruitful because they produce something, and but you don't have to. You can just say return, or you don't even have to have a return statement. It goes to the last line of the function, and it does a return automatically at the last line of the function. So here's a little bit of a rewrite of our little language program. We are going to create a greeting program. We're going to take the language as the first parameter, and instead of just doing a print statement, which is what we did before, this is now more like a function because it takes some input and produces some output it as a return rather than just printing. It's a little tacky for a function to print. And so here we return hola, bonjour, and hello based on the right thing. So now we say print greet en, so it runs the code once, lang is en, and then it runs this code, and the residual value is hello, so it says hello Glenn. And similarly, when it runs this code, it passes es in as lang, it runs through, and it runs this statement. It does, if there was more statements, it wouldn't run them. As soon as this return runs, that says that this bit right here is now HOLA. So hola Sally. And the same with French. Goes in, runs again, out comes the return statement, and then bonjour Michael. So you see how we can control as we're writing the application. We can control as we're writing the function what the residual value that we want to see in whatever expression is calling us. Sometimes we have returns and sometimes we don't have returns. So if you think of the max code that we talked about before, we can kind of see that somewhere inside that max code there's a return, and that's how it communicates the W back to us. So we pass in as argument hello world. It comes in as a parameter, and it's going to loop through this imp somewhere. It's going to loop over and over into imp, and then at some point it's going to figure something out and tell us what it wants to send back to us is a return statement, and so the W comes back and gets assigned into big. You can have more than one parameter, and they're just in order. The first one and the second one, 3 and 5. So 3 becomes A and 5 becomes B, and away we go. So we just use this to add 2 numbers, and so 3 plus 5 is 8. So you get as many as you like, and the order matters. And if you do things like you tell it you want parameters and you don't give it to them, then that'll become a traceback, and it'll blow up. You can also talk about optional parameters later. So you don't have to have return values, and that means that you simply don't call a return with a value, and return is always implicitly happening as the last line of the function. So that's kind of the basics of how functions operate, but I don't want you to get too excited about writing functions. Some programming classes are like, gotta write a function, gotta write a function. Functions, to be clear, are a very powerful mechanism. And as we write programs, 150, 200,000, 200 lines of code, 1,000 lines of code, 10,000 lines of code, The concept of a function is really important. We would go crazy if we didn't have functions. But if you're only writing 20 lines of code, forcing yourself to write a function is kind of pointless. So don't worry about maybe the lack of urge to use this. We are calling lots of predefined functions, and we will for the next couple of lectures. There will be a time when you go like, oh, I'm sick and tired of repeating myself. Oh yeah, time to write a function. So that's why we don't push functions prematurely. We just want you to know what they are, use them, and at some moment you'll be like, oh, I want to define one. But don't worry about, it might take a while before you really want to define a function. So that kind of summarizes our lecture on functions, and up next we're going to do iterations. Hello and welcome to Chapter 5, Loops and Iteration. Now we're going to work on our fourth basic pattern of sequential, conditional, store and reuse, and loops and iteration. And this is the one where we teach the computer how to do things a lot. We can tell it to do something a million times. And so that's where we get the doggedness of computers, or the fact that they're so good at doing work for us because we can set them off to a task and they'll do it until it's done. So here's a very simple loop. Let's put the coffee over here. The keyword that we're going to start using is the while loop. We're also going to use the for later on. And the while loop functions very much like an if statement. The while starts it, and then this is just like an if statement. It's a question that leads to a true or a false answer. And then there's a colon, and then there's an indented block, and then we use the de-indent to determine how long the loop is, and so this print is de-indented, so that indicates the end of the loop. And so at some level, what's going to happen here is it's just going to run, and if this is true, it's going to run this code, and if it's false, it's going to skip the code. In that way, it functions like an if. The place that it doesn't function like an if is after it's run the code once, it goes up and then asks the question again. And so you can think of it going back up kind of to the top of the while loop and then re-asking the question, like, okay, is this going to run again? And then it's going to do that some number of times, and then it's going to finish. And so that's the loop, that's the iteration. And we're going to make a variable. We're going to construct very carefully a variable that we call the iteration variable, and that's n. And it's a variable that's going to change, and it's our way of running the loop, but not running the loop forever. So let's just run this. We come in, n is 5. Is n greater than 0? Yes, it is. So we're going to run this code. We're going to print out 5, then we're going to subtract 1, and then we're going to go back up and ask the question. Is n greater than 0? And the answer is, since it's 4, the answer is yes. So then it runs again. Then it prints out 4, subtracts it again, checks, prints 3, subtracts it again, prints 2, subtracts it again, prints 1, subtracts it again. Now n is 0, and so it comes back up. Is this question has now become false? So it's going to take the exit. So it's going to come down and run this line right here. Then it prints blast off, and we can kind of print out the residual value of n just to sort of prove to ourselves that it ran until n was no longer greater than 0, and then 0 was the final value for n. And we carefully constructed this n equals, oops, go back. We carefully constructed n. We set it to 5, then we carefully subtracted 1 each time through the loop, and then we're using that to control when to exit the loop. And so you could think of this loop as, for now, running 5 times, true, 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 and then false finally. So this question was true for a while, and as long as it was true, the loop ran, and then when it turned false, the loop stopped. And so this variable that we construct to control the loop was called the iteration variable, because it tells how many times this loop is going to run over and over, or otherwise known as iterate. So this is a badly constructed loop with an iteration variable that we didn't do very well. And so if we take a look at this, we start out with n5, and then this is greater than 0, so it's true, so it runs it, and then it runs it again, and n is still greater than 0. So you can pretty much see, because we're not changing n, this is going to be true, 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 dot, 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 forever, true forever. And so this is an infinite loop. And it's just going to run until your computer runs out of battery or you hit the button. This is the kind of thing where you often see your computer spinning like a spinning beach ball or some other indication that your computer's super busy. It's in some kind of a loop really tight and it's running something and it's using up all of the processing resources of your computer. That's an infinite loop. And so the problem is we did nothing with the iteration variable. Now here's a different loop. And so this one demonstrates a different idea. So in this case, we start out with n is 0 and it comes in here. And is n greater than 0? Question mark, and the answer is false. So it skips it. It doesn't run these lines of code at all. And so this loop doesn't run at all because it comes in, asks the question, it says no, and then it skips right around it. So never run, never run. And so this actually is, sometimes you write a while loop on purpose like this, not quite as simple as this one, but the idea is this emphasizes that these loops are what we call zero trip. They are not even guaranteed to run once. They're going to run maybe 0 times. And in this respect, it functions exactly like an if statement, right? Meaning the first time through the loop, if it's not true, it's just going to skip right by it. So there's a couple of ways of getting out of loops. In this case, I'm constructing an infinite loop because remember the kind of definition of an infinite loop is if this is going to stay true. Well, true is the constant true. So this is going to run forever. And what it's going to do is it's going to prompt with a little arrow and then let us type and read whatever we type into the variable line. And then if the line is done, we're going to break. Now break is an executable statement. And if you hit the break, it exits the innermost loop out to the place beyond the end of the loop. So when this runs the first time, and we say hello there, line is not done, so it prints it. So it prints out hello there and then goes up. And then we type in again, we type finished, and so it's not done, so it prints it. So now comes that print statement. And then we type in done, and now this becomes true. And it comes out and runs the code beyond the end of the loop. The key is it doesn't go back. It's like once you've done a break, that loop is done. And so you look at basically, you know, the block that is the loop. So here's kind of the loop block. And then the break goes to the line after the end of the loop block. And you can think of this as sort of like just a hyperspace jump. There is nothing really, this could be literally hundreds of lines with if statements, and you could be running and doing all kinds of stuff and running and doing all these things, you know, and these things could run all kinds of ways, right? The point is as soon as you hit a break statement, however much stuff is down here, however much stuff is up here, it exits to whatever the next line is beyond the end of the loop. Continue is another loop control statement, but it works differently than break. So break says get out of this loop. Continue effectively says stop this iteration. We're done with this iteration. And so continue says go up back to the top of the loop. Oops. Yeah. Go up back to the top of the loop. And so here we read a line. If the first character is a pound sign, line sub 0, if that first character is pound sign, we're going to skip it. And this is a way for us to make like little comments in our typing. And then we print, if the line is done, we get out, and otherwise we print it. And so that's why there is no printout here, because it comes in, runs, oops. It comes in, this is true, and that goes back up. But it comes back and prints out the next one and does another thing. And so the loop continues, whereas the break ends the loop. And so again, the same kind of notion that you're sort of doing all kinds of complexity. Wherever you're at in this loop, you hit continue, and it doesn't go any further. It goes back up and runs the question mark. It asks the question mark. And so, asks the question, and it might exit the loop in that particular case. But this one here is this is an infinite loop that I've constructed. This is not an infinite loop because at some point the break gets us out of the loop. And so it's an infinite loop with break to escape it. And that's another common way to construct a loop. So these loops that we've been drawing so far, the ones that use while as their keyword, are what are called indefinite loops. And that's because they kind of go for a while, till a break hits or until some value becomes true. I mean, until that, as long as that value remains true. So when all the ones we've done so far are easy to look at and know that they look pretty good and they're probably going to finish. But there are sometimes, if they're long and complex and their exit or termination conditions are a little more complex, it's not clear that they're really going to terminate. And so we can use while loops for a lot of things, but for most of our looping, we're going to use what are called definite loops, and that's what we're going to talk about next. So definite loops use the for keyword, and the idea of a definite loop is it's going to loop through some set of things. It might be a set of lines in a file, it might be a set of characters in a string, it might be a set of strings in a list of strings, but whatever it is, it's sort of going to run a finite number of times depending on the thing that it's looping through. And we like this, and it's an easier way to construct it, and we actually don't have to deal with the iteration variable. The for loop includes a mechanism to construct the iteration variable for us. So it's definite loops iterate through the members of a set. So here's a very simple for loop. And so you see the for keyword, and in is also a keyword. And the iteration variable is something we put right here. This I is declared. This I is like an assignment statement. And I is going to take on successive values. So I is going to be 5 the first time through the loop. Then I is going to be 4 the second time through the loop. 3, 2, 1. So I is going to be assigned 5 different times to 5 different values. And then the loop is going to run. It's going to run once with 5, once with 4, once with 3, once with 2, and once with 1. And so this block of code we have contracted, say, execute it 5 times with these values of I. I is that iteration variable. I is the thing changing through each iteration of the loop. Okay? And so that's why this prints out 5, 4, 3, 2, 1, and then when it's done, it finishes it. And so this is a much more direct syntax for looping 5 times and setting an iteration variable. You kind of all combine it into this one thing, right? All into one thing. So it's quite nice. So you don't have to be going through a list of numbers. There's all kinds of things that we can iterate through with for. And by the way, while I'm sitting here, I named my variable friends, because that's a list of strings, and friend, which is the iteration variable. I'm using singular and plural because it helps you read it. Python doesn't understand singular and plural. So just because you say friends doesn't mean Python knows it's a list. Python does know it's a list, but it doesn't know by the name of the variable I've chosen. That's your basic mnemonic variable warning. These are cool variable names, but I don't want you to be confused by them. So you can loop through a variable, so we're going to take this list of 3 strings and stick it in friends, and so friend is going to iterate through that. So the first time through, friend is going to be Joseph. Second time through, it's going to be Glenn. Third time through, it's going to be Sally. And so that just says run this loop, run this code, the indented code, 3 times. Each time the variable friend takes on a successive version of a successive value that's in the friends array. So it says happy birthday Joseph, Glenn, Sally, and then we come out of the loop and we print done. So if we try to draw a picture of what this is really doing, the for loop is actually doing a whole bunch of stuff that we would have to do with maybe separate statements in the while loop. First, it decides how many times to run the loop, so it's answering the done question, which way do we go? And it is also then moving I ahead. It's managing the iteration variable. If you go back to it's initializing it too. If you go back to the while loop, we had n equals 0, while n greater than 0, n equals n minus 1. So we had like 3 lines to control the loop to manage the iteration variable. But with a for loop, we don't have to do that. And so that's all taken care of. And so that basically says, you know, the for loop, by you using a for loop, are we done? No, we have 5 things to work. Well, set out of the first one, run it. We're not done because we got 1 more. Set it to the second one, third one, fourth one, fifth one, and now we're done. And that is all handled in a single line of code that includes the iteration variable and the set of things through which we are going to iterate through. I really like the word in. It is mathematically, it reminds me of the set theory where you say this is a member of this set, or the for each. Math isn't important here, but if you do know math, the vertical bar means such that, right, is a member of this set, and that kind of stuff, member of this set. I'll erase the math stuff so we don't over math. But it's like, for each of the values in the set 5, 4, 3, 2, 1, run this loop setting the iteration variable I to the members of that set. So in reminds me, for those of us who are math oriented, in reminds me of a really nice concept in mathematics. Okay? Now, you could think of this as sort of this looping structure where the for loop, and this is pretty much how it actually runs inside the computer, right? Where it initializes it it runs this thing 5 times, and then executes. That's one way to think about it, but you could also think about it in a somewhat more abstract way, and think of it as all we're really doing is we have a contract with Python that says we're supposed to run this code 5 times, and I is supposed to be 5, 4, 3, 2, and 1. So you could imagine this might be what's going on. The for loop sets I to 5, runs our code. The for loop sets I to 4, runs our code. The for loop sets I to 3, runs our code. The for loop sets I to 2, runs our code. For loop sets I to 1, and runs our code. All we know is our code was ran 5 times, and by contract, each successive time, we're get a different value for I, and the value for I is taken from this set. And so this is just one way to think about it, to say to yourself, oh yeah, this is one way to think about it as it's actually, and this is how it really works. But this is also kind of logically the contract that Python is making for us. So up next, we're going to talk about taking this notion of doing something to a lot of items, but accomplishing something with that, and I call these loop idioms. So now we're going to talk about loop idioms, and loop idioms are patterns that have to do with how we construct loops. We have the mechanics of fors and whiles, but ultimately we want to get something done. We want to solve a problem with a loop. And often what we have to do is, if we have a set of things, whether it's lines or strings or characters or numbers, we're looking for something like the largest or the smallest, or we want to add them up or something like that. And so we can't just say add them up. We have to say go through each one and do something to each one and somehow achieve adding them up. And the pattern that we're going to follow is we're going to have this loop that's going to do run once for each thing, right, in some chunk of data. And then, but we're going to set something at the beginning, and then we're going to do something to each one. And at the end, we're going to kind of get the payoff. We're going to get the result. So if we're doing sort of summing things, we're going to have a running total. And so this will be like t equals 0. And then this will be t equals t plus the thing value. And then, but this is not the real total. It's the running total during the loop. But at the end, it is the real total. And so we're gonna look at what you do at before the loop starts, during the loop, and then what you get after the loop and how you can use that. So we're going to use this loop. It's just going to loop through a set of 6 numbers over and over and over again, right? So we're going to do something before the loop, we're going to do something after the loop, and then we're going to run the loop some number of times. And in this case, thing is our iteration variable because I'm using unmnemonic variables now. So it's going to run 9, 41, 12, 3, 74, and 15. So it's going to run and print these things out. So it runs this loop 6 times, and away we go. Now this loop does nothing except print stuff out. Of course, I like to do that first, is always print things out to make sure that sort of my brain is functioning. So to kind of understand how these loops work, I'm going to ask you to function as a program. And I'm going to show you some numbers in succession, and I want you to mentally figure out what the largest number is, but more importantly, think about how your brain is solving this problem of what is the largest number, given that I'm only going to show them to you one at a time for a little while, and your brain has to do something. And imagine I was going to show you thousands of numbers. I'm not, but imagine I was. How would you organize yourself in a way so that for like an hour and a half, you could sit here as I showed you numbers and you keep track of the largest number that you've seen of all the numbers? Okay, so here we go. Here's your first number. Second number. Third number. Fourth number. Fifth number. Sixth and last number. What was the largest number? What was it? Well, it wasn't too hard. It was 74. But that's not the question. How did your brain arrive at 74? So here's all the numbers. If I'd shown you all the numbers and asked you what's the largest number, your eyes would have sort of gone, and then you got to 74. And you wouldn't do it in any particular order. Your eyes would just like see the 74 and it would just throw smaller numbers away, and it would move really quickly to what the answer is. Even if there was several hundred numbers on the screen, your mind would sort of move fluidly wherever it felt like moving and then arrive at it. And probably what it would do is it would do something like, you know, kind of move like this, find this, and then sort of check to make sure that it's okay, and then say like, okay, I got 74, I'm done. That's not how computers do it. That is not how computers do it. They do not move fluidly. But they are highly dedicated. They're going to do something. 74. But how would you construct a loop to achieve this? So let's take a look. You could create a variable called largest so far. And this is the largest variable, the value that you've seen in the list so far. Now, I haven't shown you any numbers yet, so we'll just set this to -1 to get us started. So now we see 3. And we're like, oh, that's better than -1. It's our first number, so it's probably the largest we've seen so far, right? Great. 41. Oh, that's bigger than the largest we've seen so far, so we'll keep it. 12 is not bigger than 41, so we're not going to keep it. Notice this keeping thing. 9 is not bigger than 41, so there's no point to keeping it. 74 is bigger than 41, so we'll keep it. Is this the largest number? We don't know. We don't know until we're done. 15, not better than 74. So now we're all done, and hooray, 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 we have the largest number. And we had this variable that we kept the largest number that we'd seen up to this point. And then when we know that we're done at the end, then that becomes the largest. So if you look at all the numbers, keeping track of the largest so far, at the end of all the numbers, the largest so far and the largest are the same thing. And so that's how you get this idea of something you're doing during the loop is not really the answer, but by the time the loop is done, you will have the answer. And so here's a bit of code that does this. Use it with our numbers, right? So let's take a look. So I have this variable called largest so far. I set it to -1. Before the loop, remember there's a loop before and a loop after and a loop in the middle. Before it's -1. So now the num, remember underscores are okay, that's my iteration variable. If 9 is greater than largest so far, well, largest so far is -1, so that's true, so this code's going to run. So we're going to remember the new number. So this is 9, and so 9 ends up in largest so far, and then we print it out. And so largest so far is 9 after we saw the number 9. Then we do it again. So now 41 comes in. And is 41 greater than 9? The answer is yes, it is. So we're going to run this code, copy 41 into 41 into largest so far, and then print it out, and largest so far is 41 after we saw the number 41. Now we're going to run the loop again with 12, okay, and you get the idea, I hope. Is 12 greater than 41, which is the largest we've seen so far? And the answer is no, it is not, so we skip. So the largest so far stays 41 even though we saw 12, meaning we're sort of like ratcheting up, but we never ratchet back down. So we run it again with 3 and 41, and we skip this, and then the largest so far is 41 even though we just saw 3. And now we see 74. Is 74 greater than 41? See, we never are looking at all the numbers. We're only looking at the window on the numbers of the current number that we're looking at. So is 74 greater than 41? The answer is yes. So we run this code and then we capture the 74. So we just saw 74 and it is the largest so far. And then we run it again with 15, but 74 is our largest so far, and so it skips. So 74 remains largest so far, after 15, and now we're finished because we just ran the last thing. The for loop takes care of everything and jumps to this print statement and says afterwards, largest so far is 74. But at this point, it's also the largest, right? So largest so far became largest when our loop finished. So that sort of gives you this notion of how we construct, something at the beginning, some kind of thing that we're going to do over and over and over again, and then something at the end. And we put some print statements in just so we can watch it and see what's going on. So coming up next, we're going to talk about some more loop patterns, some counting, totaling, averaging, and finding the smallest number. So now we're going to look at some more patterns of the different things we can do at the top of the loop, in the middle of the loop, and at the bottom of the loop. And the first one we're going to do is counting. Now we're going to take a look at the number of something, the number of things in our list. Now we could just inspect it and see 6, but you will have for loops like you're reading through a file or scanning through some data. And so the notion of counting, you have to assume that you don't really know, that there's going to be a lot more than just 6. But for now, we're just going to do 6, and we're going to count how many things that we see in this loop. And the pattern is simple. You set a variable, Zork, to 0 at the beginning. We often call this variable count in mnemonic. And now we're going to run this loop 6 times, 1, 2, 3, 4, 5, 6, and each time through we're just going to add 1 to Zork. So Zork starts at 0, then it goes 1, 2, 3, 4, 5, 6. And we're going to print it out. So, we see the 9 and Zork is 1. See 41, Zork is 2. And Zork is 16. When we see the 15, 4 stops, and we print out afterwards. And this then is 6 is then the ultimate count that we got. So that's very, very simple. The pattern is that set it to 0 at the beginning, add 1 to it, and if you run that enough times, then this is how many times that happened. And in a sense, it's how many times this line ran, right? Sometimes you put this in an if statement, etc., etc., etc. Okay? Oops. Now, we can do the same thing to get a total. And the way the total works is you compute a running total of the number of the items that you've seen so far, and at the end, the running total, in effect, becomes the total. A better variable name for this would be like sum or total or something, but Zork, I'll use Zork again. So you set Zork to 0, and it starts out, the total we've seen so far is indeed 0. And then we're going to run this 1, 2, 3, 4, 5, 6 times, and thing is going to be the iteration variable. It's going to take on the successive values, and each time through we're just going to take our running total and add to it the thing we've seen. So we see 9 and the running total is 9. We see 41 and the running total becomes 50. We see 12, the running total becomes 62. We get a 3, it becomes 65. We get 74, running total is 139. How many more are we going to see? We don't know. Could be a million, could be 1. Oh, it's only 1. We get a 15, our running total is 154. And what's true at any moment here is the running total is right up of what we've seen so far. Now, when we're done, the for loop quits for us, and afterwards 154 is indeed the total. So the running total while we're in the loop, at the end of the loop, after the end of the loop, we have the actual total. So it's not very difficult to convert this to the average because we've calculated the count and we've calculated the running total, and now we're going to have the average by simply dividing those. Okay, so now this time I've used mnemonic variables. Don't get confused by this. Mnemonic variables are just friendly names I chose for you to read the code easier. I am not communicating to Python in any way by naming this count and sum, but count and sum is nice. Okay, so I set count to 0 and sum to 0. Oh, go back up. I set count to 0 and sum to 0 at the beginning, and the count is 0 and the sum is 0. And then I'm going to run this loop 6 times, 1, 2, 3, 4, 5, 6, and each time value is the iteration variable. I count, every time I run the loop, I count equals count plus 1, sum equals sum plus value, so I have a running count and a running total, and they show up here, 1, 2, 3, 4, 5, 6, and then the running total. And then at some point, the for loop, we do the last one, and the for loop jumps out, and it divides 6, 154 is the count and running total, and then it divides the average sum over count. Okay? So that's just, again, a pattern of something in the beginning, something in the middle, something in the end. Another kind of thing we tend to do in loops is we look for things, we hunt for things. And so this is where we have an if statement inside of a loop. And of course I've created a silly simple thing. In this code I am looking for large values that are greater than 20. And again, don't think of this as just 6 numbers, but I'm looking for all the values and I'm going to print them out. So, it says before, it's going to run this 9. Well, if 9 is greater than 20, it's false, so it goes back up. 41, true, so it prints out 41, then goes back up. 12, false, goes back up. 3, false, goes back up. 74, true, so it runs this, so out comes that little print statement. Goes back up, and then 15 is the last one, and that's false. It goes back up, and the 4 says, we're done, and then we do afterwards. And so this is just the notion of having an if statement inside of a for loop, where we're sort of picking or choosing or selecting or looking for something in a large set of things that we're looping through. We can also say, I want to know if a particular value is there. And so we're going to use a Boolean variable. And we've talked about integer variables like 1, 42, and then floating point variables like 98.6, and then string variables like hello world that have quotes in them. This is a fourth type, a kind of variable. It's called a Boolean variable, and it only has 2 values. It has true and false. Matter of fact, these if statements, they return Boolean values. Value equal 3, that is returning a true or a false based on the value of value. There's a mnemonic confusion there, right? But I'm using it. So I'm going to make a variable called found, and that's a decent name for a variable, so don't get hung up on that. And I'm going to initially say found is going to indicate to me whether or not I found a 3 in my list. And I'm going to start before the loop starts, say false, because we haven't found anything yet. So found equals false. And so at the beginning of the loop, found is false. Before the loop starts, found is false. And now we're going to run this loop a bunch of times. 9, is that true? No, skip. 41, is that true? Skip. 12, skip. Right? So 9, 41, 12. And found has remained false because we haven't done anything to it. But now in comes a 3. And this becomes true. So it runs this code. So found becomes true. And then we print it. And you'll notice that when we see a 3, we get true. And then it runs again. We get 74. It's still false. 15, it's still false. Run, 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 quit. And the residual afterwards is true. And in fact, if you didn't know any of this and you don't print that out, all you know is that afterwards we loop through all those things and we know that there was a 3 in there. That's what we're doing. So we searched all of them, we checked for 3s when we found a 3, and you can see basically that, the found remains false until it flips to true, but then there's nothing to set it back to false. There's nothing in this loop that's going to set it back to false. So once it sort of catches the 3, then it remains true for the rest of the loop, and then it just finds its way out. Now, if you want to think about it for a moment, ask yourself, how might we make this loop more efficient by putting a statement right in here? Think about a way to, once you've found it and it's true, there is sort of no reason to keep on going. So what would you put there to perhaps make this loop to look for 3s, just to tell you whether or not there was at least one 3 in there, how to make that more efficient? Just think about that. Okay, so now let's look back at the largest value that we started out with, right? And so if you think about this, let's kind of give it a sort of a rough look here. Largest so far is our kind of like a running total, but it's our hypothesis is the best large number. And we have this if statement that says if the number we just see right now is greater than the largest so far, then capture it, right? Take whatever number we saw and capture it. So when we see 9, it's better, we capture it. We see a 41, it's better, we capture it. We don't capture this, we don't capture this, but we capture the 74, and we don't capture the 15, and that's how we do it. So you could think of this as better. When the number we're looking at is greater than our working hypothesis of the largest, we grab it because it's better. So this line right here is the grab line. Grab it. Okay? So then the question is, how would you modify this code to teach it to find the smallest value in this list of numbers. Think of it as you have a starting number, you have a sort of what's better in this grabbing notion. How could you do that? Take a look. Okay, so let's take a look. So let's do a couple things. Like if you look at this if statement, that's better. Well, it's better now if the number is less than. So but then we should probably change this to be smallest so far, 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 right? Matter of fact, that's what this is. We've changed the word largest so far to smallest so far, and we've changed the greater than to a less than. Is that going to fix it? I'll give you a second to look at it. Pause if you need. Is that going to fix it? Is that going to find our smallest number? The answer is, of course, no, it's not. So if we run this code, so we set the smallest so far to -1, and it starts out -1. We run it, and it's 9. Is 9 less than -1? No, it's not. So after we see a 9, the smallest so far is -1. Now we're going to run 41. Is 41 less than -1? No, it is not. So the smallest so far is still -1. As a matter of fact, it isn't the smallest so far anymore. Just because we named it smallest so far doesn't mean it is the smallest so far. It didn't work out so well. And so you see that none of these, because they're never less than -1, do anything. And we claim that afterwards the smallest we've seen so far is -1. And that is because, of course, -1 is smaller than any of the numbers that we saw. So how could we fix this? Well, if we started the smallest so far with some like arbitrary big number, then it'd be better. So if we made this 100, whoops, come back. If we made this be like 100, that'd be good, because the first time through, the 9 would be less than 100, so we would capture the 9, and then the rest of the loop would work just fine. But then what if we didn't know how big these numbers were? As a matter of fact, the largest so far wouldn't have worked if all the numbers were negative. Think about that. We just assumed they were positive, and so we kind of wrote lazy code that assumed all numbers were positive. That might not be a good assumption depending on the numbers that you're dealing with, right? So maybe 100 is a good number to start with, or maybe like 1,000 or 10,000, or like some number with lots of zeros in it. How big should we make this? And the answer is we're kind of solving this problem the wrong way. And the thing we really want to do to solve the problem is to just accept the fact that if we're looking for the smallest number so far, that the right hypothesis is the first number. And if we just knew what that first number was, the 9, because it's the first number, we know that it's both the largest so far and the smallest so far as soon as you see the first number. But we don't know here before the loop starts what that first number is. I mean, you can look at it, but assume this is just data that's coming from somewhere else, and we don't know it until we start reading it. So we have to construct a loop that deals with the fact that we want to capture the first value as our hypothesis for smallest so far. So how do we do that? Let's take a look. So what we do is we use yet another type. So we have integer, floating point, string, Boolean, and now we have a thing called the none type. None type is a special marker in that it only has one value. Boolean has true and false. You know, floating point has an infinite number of values, and integer has an infinite number of values, but none type has one value, none. None is a constant. Capital none is a constant. The difference is we can check to see if we have stored none. None is often used to indicate emptiness, not non-existence, because smallest doesn't exist until we assign it, but we're going to assign it to like a mark, a flag, a marker, some way to say, oh, this is not even a number, it's nothing. And so we're going to, and you can do this. So that's like makes a variable called smallest, and in it puts none. It sticks it right in. It's not a string none, it's like a special type. Okay? So that actually captures the notion that before the loop starts, the smallest number that we've seen so far is none. We haven't seen any numbers. Okay? So then we come in and we have an if statement. And we have a new operator called is. Is stronger than equal sign. And so if smallest is none, that becomes true. It runs this case. And so then what it does is it copies this first value, which is 9, into smallest. And so we see a 9, and the smallest so far is 9, which is the first value. And again, we're assuming we don't know what the first value is before the loop starts, so we use the first iteration through the loop as the moment where we capture that. Okay? So, smallest is the value, and then we print it, and we go back up, and now it runs again with 41. 41 is not none. There's only one thing that's none, so it is not equal to none. Smallest is not equal to none, or is not none. So this is false, so it skips over here. Then it asks the question, is the value we're looking at, 41, less than smallest? Well, smallest is 9 in this case, and this is 41, so that's false, so it skips that and goes on. So we see 41, we don't take it, and then you can see that this will never become true again. This is pretty much false for the rest of the iterations of the loop. It's false for the rest of the iterations for the loop. So it just is going to run down here and ask this question. And at some point we see a 3, and we run this code, we capture it. We see 74, we don't capture it. We see 15, we don't capture it. So then the for loop skips out. At the end, we have the smallest. And actually, this would be a good technique for the largest as well, because it really is just a technique to put a marker in this variable so that we snag that first number or first whatever as we read and parse through them. So the is and is not operators are very useful in Python. You can think of them as like the double equal sign. They're asking a question, and they return a true or blank is blank returns a true or a false. It is stronger. Double equal says, are these things equal in type and value? So just as an example, if I were to say, is 0 equal to 0.0, it would say, yeah, that's true. But then if I says 0 is 0.0, that would be false. So that's because these two are the same value-wise, and these two are not the same type-wise. So is stronger than equals, meaning that it demands equality in both the type of the variable and the value of the variable, and no conversion is done. And so that's just a very strong. Don't overuse is. If you're dealing with numbers or even strings, use double equals, don't use is, because sometimes it gets a little confusing. So use is sparingly. I tend to only use is on Booleans and on none types. I don't use is on integers, and I don't use is on floats, and I don't use is on strings. Just none or true false. And also is not is also an operator. So you just say blah 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 is not none, or blah 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 is not false. Okay, so we've been looping around and doing loops and loops of loops. We looked at the indefinite loops, the while loops that kind of run for a while. The definite loop, and we looked at break and continue as a way to either escape completely from the loop or go back up and discard the current iteration of the loop. We looked at none. We looked at Boolean variables. We have for loops, definite loops, where you've got some kind of a set or a list or some kind of sequence that you're looping through. And then the concept of loop idioms, where you do something at the top, something to each item, and then you sort of get a benefit at the bottom. And so that gets us through iterations. Hello and welcome to Chapter 6. In this chapter we're going to talk about strings. And Chapter 7 is the payoff chapter, so we, up to this point, we're still learning sort of basic building blocks, and actually we're going to write a real program in Chapter 7. So just learn this, and the payoff's in Chapter 7. So we actually been using strings from the very first lecture, because if you print hello world, well, that's a string. And so we've been doing things. This slide here is all review. We use plus to concatenate strings. We use print to print them out. Print's just a function that takes as a parameter something, strings, integers, etc. We can put digits in strings, but we can't add to them. By now you figured this out, but you can use things like ints to convert the strings to integers and then print things out. So, you know, we've been doing this for a while. We've been talking about strings all along. Now today, what we're going to do